Hello, Mr. Ryan. How are you today?
Good.
Good. Okay. What did we talk about yesterday? What? Left.
Something about the binary tree.
Yeah, left bottom binary tree value, right? Huh? One.
Today
Two.
we're going to talk about the right talk.
Okay. So
Today we're going to do deficit.
so we want to find out the first node, the leftmost node of the last row. Okay? Yeah. And yesterday we talked about the breadth search, right?
Today we're going to do deficit.
Level by level. And every time we expand the nodes on the next level, we store the answer as the first node, alright? And when the breadth search exits, the answer will be the first node, the leftmost node of the last row, right? Am I right? Yeah? And today we're going to talk about depth search, right? Depth search. So what's the idea of our depth search?
Go that deep as you can.
As deep as we can. And how do we know? How does it work if we use the depth search to solve this problem? How does it work?
I think you go as deep as you can, so you go to 2, and then that's
Yeah. So do we need some kind of data structure to store what kind of data, and then we can use it later to get the leftmost node of the level, the maximum level, alright?
stack.
Yeah, but we don't actually need to use the step because we can use the recursion, right? Right? So here, Eric, stop doing that. So here, Eric, what kind of data structure do we need to use to store the mapping, the level? We need to store the level and which the leftmost node, right? Leftmost node. Alright? Eric, right? Yeah? So here we can go as deep as you want, right? As we want. And then when we visit each level, we check if a node has been visited. If this level has been visited or not, right? If we go to the left first, the node, every depth search, if we travel visit the root, the node, left, right. What's this? Node, left, right. What's this order?
Deficit.
Yeah, depth search we
Pre-order.
pre-order. Yeah, if we follow the pre-order, the first node in each level will be the leftmost node if we visit it first, right? So we kind of need to remember that if we have visited the level before, right? For example, if we visited 1, have we visited level 1 yet? No.
No, I
Then-
think that's level 0.
Okay, level 0. Have we visited level 0? No, we haven't got anything in the what kind of data structure. Then we put it, set or notebook or hash map. We put it. We can make it. Okay. The level 0, we have node 1. Okay, then we go to what? 2, right? Yeah. Have we visited level 1? No. We put out the level 1 to node 2. Okay, and then what's next?
3.
Have we visited any node in level 1?
Yeah.
Yeah. So we don't store, or we don't update. Have we visited the node in level 2? No. Okay, so we set 2 equal, the node is 4. Have we visited the node in level 2?
Huh?
Have we visited the node in level 2?
No.
Yes? Then we stop. Okay, now we have this mapping, hash map. Level 0, the leftmost is 1. Level 1, the leftmost is 2. Level 2, the leftmost is 4. So what should we do now?
The last one.
Why is the last one? We find out,
Because that's the bottom, the most bottom.
and then
And
which has the, what? What's this?
because it is the bottomest. And
It has the
this
largest key, right?
Yeah.
Largest level.
Yeah.
Then we find out the value which has the largest key, right? Yeah? Yeah? So does it make sense? We use the recursion. Visit the left node, the current node, and then the left node, and the right node. That is the pre-order. And that's implemented in recursion, yeah, which uses the step by default, right? Recursion. And then we kind of need to use a hash map to store the mapping. The keys are the levels. The node, the value are the node of the leftmost node. And then at last, we need to find out the node which has the largest key, which will be the leftmost node in the largest level. Alright? Does it make sense? Yeah? Okay, can we write it, please? Can we write it? Okay. Define. Okay, let's say this function is find leftmost. Okay, the root. If not root, again we need to check the spatial corner case. Return what? If the root is empty, if the tree is empty, do we have the leftmost node in the?
No.
No, we return none. Or actually, we don't need to put a none. If we just return, it means none, right? You can also say return none, or you can just return. It means return none. Okay. And now, I need a hash map to store the mapping. So, let's say data. Let's call it data. Okay, data equals the dictionary. Okay, that's the dictionary. That's the hash map. Okay, curly brace. Okay, and then now we have define a depth of search. Okay, and then how many parameters I need?
Curly braces.
How many parameters do I need to provide in the depth of search? What? Depth of search normally start with what?
0.
No. What I mean is depth of search. We need to pass what kind of parameters in this function recursionally. If we go down to the next level, we need to pass what? What value? Eric? What's the parameters? What's the thingy? Root. Yes. And then we need to also need to pass which thing? What kind of information do we need to pass into when we visit the left node, left right node? What are we trying to do here? The what? What happened to the? If we go down to the left node, what happened? Yeah. What happened? If we go down the left node, what happened? This is level 0. What happened?
The level goes up.
The 1. Yeah. Okay. So that's the level. Yeah. And what's missing?
Column.
Okay. Now look, if root is none, yeah, we just return, yeah, we just return. Okay, then here I want to access this, so I need to put a non-local keyword to say, okay, I want to update the value in here, data. And then look, if I need to check if this level. Okay, so Eric, what do I need to check? I know this is level, and then I want to check if the level is in what? In which one?
Is the level is
has been visited, right?
Yeah.
So what should I do here?
If level in data.
Yeah, we're done. If level in data. If level not in data, okay? If level not in data, then data bracket. This is what? Square bracket. Level equals what? Root. Yes. The level. So we have the mapping level, and the root, the node. Okay, the root. Okay, then now we need to visit the left or right first. Alright. Depth of search what? And depth of search what?
Left, right.
Okay, root or left, yeah?
And root or right.
Root or right. And then what's the second parameter? We go down, what happened?
Level.
Level what?
Plus
Plus what?
1.
And here?
Level. Plus 1.
Yeah, because we go to the left, level plus 1. We'll go to the right, level plus 1. Okay, and then here we go to DFS. We call this function root, and at the beginning, what?
0.
Yes. And okay, that's the interesting part. After this bit, the data is the dictionary. We have the keys and the values, and we want to find out the keys. What are the maximum keys?
Return.
Okay, look at data dot keys. That's the keys, yeah? And if I put a maximum, what does it mean? I got a maximum level, right? Alright? Maximum data dot keys is the list of the keys. So which will be 0, 1, 2, right? Alright, after this. Okay, for example here. So what happened here? What happened after this? Can you, if this is the binary tree, so what's in data after this? At this point, what's data in here? Can you provide me data? What's in data?
As in the like level and.
Okay, 0 is what?
1.
1, and then?
1 is 2.
Okay, and then?
2 is 4.
Okay. Data dot keys returns what?
Return the last. The
Data dot keys.
keys.
Which are the keys?
The
What are the keys of? Is this one or this one? What are the keys? Key value. Which are the keys?
key value here.
That's the value. That's the key. Key value pair. So keys will be 0, 1, 2 like this. Yeah, this. And maximum returns which one? 2. Okay. And then I want to get the 2 of the 4. How can I write it?
Value.
No. This is the max. This value is max data keys. So I want to reference the value of these. So what should I do?
Return both of them.
I can just do this data and then bracket. Remember the dictionary. The dictionary. If a dictionary, I can do this data. Alright. Okay. Data 1 equals what? What's data 1?
Data 1 equals 2.
2. Yeah. Look, this is the key, and then return the value. That's the dictionary. Okay. That's the hash map. Okay. We can just return this one. Yeah. Return this one. Yeah. Dot value. Yeah. If we want to return the value, dot value. If you want to return a no, you can just do it. Okay. Does it make sense? Yeah. I'm going to erase some bit. Okay.
No.
Okay. I'm going to erase this bit.
No.
What? What should I do here?
Okay.
What should I do here? What should I check if the no? If what? If yeah. If what? You don't need to write so hard, okay? If what? If what? The current level is not in the in the data, right?
What's
It's not
current
level, which is what is the level? Level.
level?
Yeah. Not in. Yeah. Data. Okay. That's it.
I knew it.
So, yeah, data or data dot keys. It's okay. It's both okay. You can just write data. Okay, that will be. Yeah. Okay. What's the time complexity? What's the time complexity? What's n? What's the space complexity? What's n? Yeah, it's the same. N is the number of nodes in the binary tree, and we are using additional data. Yeah, hash map. Yeah, hash map. What in the worst case? How many items can be in the data? How many entries? No. If there are n numbers nodes in the binary tree, what's the maximum? In the worst case, what's the n? Why is that? Can you draw a tree which has n thingy? Yeah, you see, one level, one node, right? So in this case, data will contain n nodes. Okay, very good, very good. Okay, see you.
Bye.